Welcome to your lesson on static electricity. Let's get started. So first of all, we need to do a quick review of what you learned back in our chemistry unit. Just a reminder that you've got neutrons and protons that are in the center, in the nucleus, and then far, far away from them you have the electrons that are orbiting out around the outside. The neutrons are neutral, that's why they're called neutrons. They have a zero charge. The protons are positive, the electrons are negative. It's really key that you remember that. And remember that as well, that if you change the number of protons, you're going to change the actual element itself. So in all of the stuff that we're talking about with electricity, we're not talking about changing the nucleus. If you have a nucleus of an iron atom, you don't suddenly have a nucleus of something else. You're going to keep the positives the same. And you're also going to keep the neutrons the same. We're not going to change the mass of the atoms. But what we are going to do is steal electrons. Electrons are going to be moving. So it's only the electrons that can move from one atom to another. Just a reminder, if you change the number of neutrons, you have created an isotope. It has very similar properties to an element with more or less neutrons, but it just weighs more or less. So if you add neutrons, it weighs more, and if you take them away, it weighs less. So you get an isotope if you mess with the neutrons. You get a different element if you mess with the number of protons, and you get an ion when you mess with the number of electrons. So what we are doing is talking about ionizing atoms, ionizing molecules. So only the electrons are going to be moving for our entire unit. And that's where we get the term electricity from. Electrons moving, that's electricity. Now, if you're a metal, remember that vast majority of the elements on the periodic table are metals. They can conduct electricity very easily. That's why we call them conductors. If you added electrons to a piece of metal, those electrons are going to spread out over every metal atom that is close enough to share the electrons. So they're going to share all those electrons, and they're going to do that through something called metallic bonding. Those electrons, extra electrons, will just spread out over the entire surface. But all of these guys are going to be able to share the electrons that you give to them. That's why they conduct. Nonmetals, on the other hand, do not conduct electricity easily. If you were to put electricity into a nonmetal, you would more likely see it burn than you would see it actually transfer the electricity. That's why we call it an insulator. So you get conductors that allow electricity to pass, and you get insulators that prevent the electrons from moving. If you were to add electrons to a nonmetal, it would not be shared by all of the atoms. In fact, the charge would stay in one spot. It would not spread out over the entire object. Now, these are mostly gases here: nitrogen, oxygen, neon, argon. But you also get your solid, something like carbon would be a solid nonmetal. Most of the nonmetals and metals that we'll be dealing with are probably not going to be just a single element. We're not just talking about the gases. The nonmetals will be parts of compounds. So same with the metals, they'll be parts of compounds. Just a reminder as well that metalloids are those weird elements on the staircase on the periodic table, and some of them conduct better than a nonmetal, but they don't conduct as good as a metal. So we call them semiconductors, and these are extremely useful, especially silicon. They are very useful in circuit boards. When you don't want the electricity to overload the entire circuit, you want to slow it down and allow the electricity to do some work for you, you're going to use a semiconductor to do that. So silicon. So what is static electricity exactly? Well, when the negative electric charges build up on the surface of a non-conductive material or an insulator, that's what it is. An insulator doesn't allow electric charges to move through it. They're going to stay put. So if you throw some negatives onto a surface, they're going to stay exactly there until they can be discharged. And we'll talk more about that in a second. When electrons get added, the more electrons you have compared to protons, you should get a negative charge. You should realize that. When you remove electrons, you now have less electrons than protons. Your overall charge should now be positive. If you don't change them, you just leave them alone, you have an equal number of electrons and protons, then your overall charge should be neutral. You can either write it with an N for neutral or a 0 to show that there's a 0 charge. So negative, positive, 0 charge. And again, we're not changing the number of protons, we're only changing the number of electrons. That brings us to the law of electric charges. Please memorize this. It's very simple. This right here is the law of electric charges. Like charges are going to repel. So because this object is negatively charged and this one is negatively charged, those are like charges, they will repel each other, they'll push away. Same thing with positive and positive, they will push away. Unlike charges, on the other hand, will attract. This is the same idea as saying opposites attract. So if I have a positive and negative together, they'll pull together. But that'll happen as well even if I have a neutral object. The neutral is attracted to the positive object, and the neutral can also be attracted to a negative object. This is why playing with balloons in your lab, you're going to be rubbing it on your hair and causing the balloon to stick to the wall. Keep in mind, though, that because the neutral objects do not have an actual charge, they can't attract or repel another neutral, even though they are like charges. They're not going to repel anything because they are neutral. They don't have any charges. The only reason that this combination over here with the positive and neutral works is because the one object is charged. And same thing here. This is charged, so it will attract, but it's not going to be able to attract if there's no charges whatsoever. Okay? Now, here's the main thing, charging by friction. This happens when any two different materials get rubbed together. One of those materials is going to have a higher electron affinity, or we can say higher electron attraction, and it will steal or rip electrons from the other material. So that means that if I can rub the two together by friction, I can get one to have a greater charge, a greater negative charge, and the other will then obviously have lost electrons and it'll have a greater positive charge. I'll show you an example in a second. Somebody at some point in time, maybe many somebodies at many points in time, have gone through and they've created a massive list. Now this is just a short snippet of the big list called the electrostatic series or the triboelectric series. And what they've done is they have put them in order of who has the strongest at the bottom in this case, strongest hold on electrons versus weakest hold on electrons. If they have a weak hold on electrons, we would say that they are less electronegative, and they're going to lose their electrons easily, which means they become positively charged. If they are more electronegative with their strong hold on electrons, then they're going to gain electrons very easily and they'll become negatively charged. But this is a relationship. So, for example, if I was to compare opposite ends, so the acetate versus the platinum or the gold, because the acetate has a weak hold on electrons and the platinum and gold have a very strong hold on electrons, we can expect that the acetate will give up its electrons to the gold and become positively charged. And then because the gold will have extra electrons, it will become negatively charged. So it's very obvious when you look at the other ends of things. But if we start to compare things that are more towards the middle, it all becomes about the relationship. Now, whereas acetate, because it's less electronegative than the wool, would give its electrons to the wool if they were rubbed together, the wool is less electronegative than, let's say, cotton. So if we rubbed wool and cotton together, then this guy, the wool would become positive and the cotton would become negative. Even though in this situation, rubbing the acetate with the wool together, this guy would have become negative. It just depends which ones you are comparing. The wool versus the cotton is why when you take off a wool sweater, you get a lot of static. It's because you are rubbing the materials together. The wool and the cotton are your cotton shirt and your wool sweater are being rubbed together as you're pulling it off of your body, and they're charging by friction, and the wool becomes positively charged and the cotton becomes negatively charged. Okay, so here's some comparisons. You're going to do this as a little assignment next. Let's compare rubber versus silk. So we go up and we look for them. There's silk and there is rubber. Rubber is more electronegative, so it should become negative, and then the silk should become positive. If you're looking at silk versus cat hair though, hair is less electronegative, has a weak hold, so it'll become positive, and then the silk will become negative. Silk negative and hair positive. And then the rubber versus wool. Rubber is more electronegative than wool, so rubber will become negative. It'll steal electrons. And then cotton versus acetate. There's the cotton, there's the acetate. Cotton is going to steal electrons from the acetate. Okay. Now, which of the above pairs would produce the strongest charge? Well, now you have to look at how far apart they are on the table. The closer they are, the less difference it'll have. So if you were to rub your hair with wool, for example, you might build up a very small charge, but not as big of a charge as if you had the wool versus the cotton. So if they're close together on the electrostatic series, then they're not going to have a huge difference, but the farther apart they are, the more difference you'll have. So if we look between rubber and silk, well, they're 6 jumps away from each other. The silk and the cat hair were only 2. They're quite close. Rubber and wool are 9. Cotton and acetate are 7. That makes the rubber and the wool, because they are farthest apart in the electrostatic series, they will have the strongest charges built up. So the rubber will become very negative and the wool will become very positive from all the electrons being stolen. Let's flip now to an example. This is my beautiful artwork. I hope you enjoy it. Here's an example of charging by friction. And I'd like you to try this today. If you guys have a balloon, or if you have a plastic comb, this will work as well, although it's more fun with a balloon. When you first start out with the balloon and your hair, you've got an equal number of charges. This is a neutrally charged balloon, so it has an equal number of positives and negatives. And your hair is actually also, unless you've already got some static in it, it's also neutral. So you can count and see there's an equal number of positives and negatives. When the balloon gets rubbed on your hair, because the rubber of the balloon is lower on the electrostatic series, it has a higher electronegativity than your hair does, it will steal electrons from your hair. So they'll transfer to the balloon, but they'll only transfer to the exact spot that was rubbed on your hair because the balloon is an insulator. So once the charges land on the balloon, they stay there. It's a very localized negative charge. The rest of the balloon is still neutrally charged. It's only this section right here. The positively charged hairs that you left behind are now, because they are like charges, they're going to end up repelling each other. So the charge of the balloon, and that's why your hair is going to stand up. The charge on the balloon cannot flow through the balloon. It must stay put or be static because rubber is an insulator. And that's why we call this static electricity. Static just means to stay in one place. So the charges stay where you put them until the extra electrons have a chance to jump to another object. When they leave the balloon, we call that discharging. If you were to put your hand on the balloon, right where the charged area was, you would hear the little crackling sound of the electrons jumping, the little mini lightning strikes, and you would have the balloon become neutral again. You would have discharged the balloon to your hand or to, let's say, a metal doorknob or whatnot. Now, the balloon electrons are able to jump to either a positive object because they are negative. They can jump to a neutral object, which means they would now charge the neutral object and make it negative. Or they can jump to the ground. The ground is considered to be overall neutral because the Earth is just so massive. It's such a vast size that any charges you throw into the ground are negligible because there's so many positive and negative charges. You're not going to be able to charge the ground. It's very, very difficult. You can do it in a little local area for a short period of time, but very, very soon you're going to get charges all balanced out again and everything will be neutral. Your positive hair then can also be discharged because what you want to do is for the hair, you need to give it back electrons so that it can go back to being neutral and it will come down. And you can do that with a negative object. If you had extra electrons sitting on another object, you could give it back to your hair. You could do that with a neutral object. Or again, you could do it with the ground. So those are ways to discharge. If you guys could take a look and see the little lab that has you rubbing your hair with a balloon and get that performed, then you will be doing good for today. Thanks for listening.